Hey everyone, my name is Rahul, and this is part one of my three-part series on the breadth first search algorithm, also known as BFS. In today's video, we're going to be going over what BFS is, when you use BFS, we're going to go over some examples to show you what BFS looks like on certain inputs, and finally, we're going to go over some of the properties of BFS. But that's not all. Next week, we're going to release part two of my three-part guide where we talk about how you code BFS in Java. And finally, the week after that, part three, where we're going to talk about some interview tips for BFS. If you end up liking this video, please share it with a friend and leave a like down below. It's a free and easy way to support my channel. And consider subscribing for more content like this, or if you're really interested in parts 2 and 3 to make sure you don't miss those. Without further ado, let's get straight into it. Just a disclaimer before we begin, the word node and vertex are going to be used interchangeably throughout this entire presentation. They mean the exact same thing, so if you hear one or if you hear the other, just remember that. Before we jump into some examples, let's first talk about when we use BFS. We primarily use breadth first search on a graph-like structure. A graph-like structure is any structure that has a set of vertices that are connected to each other by edges. This can also be in various different forms, and that's why I have a tree up here as well, because trees are a graph-like structure. So be aware of that. Any graph-like structure can be used to run BFS. Let's jump straight into an example. Here we're going to be looking for a path from node A, which is our starting node, to node B, which is our destination node. We're first going to start off at node A, and we're going to ask ourselves, is node A the destination? No, it's not. We're looking for node B, so we're going to go ahead and mark node A as visited. By marking it as visited, we're making sure that we don't come back to node A by taking some kind of a path through this graph and then trying out its possibilities again. We've already visited it, there's no need to come back here. Then we're going to go ahead and visit the nodes that are adjacent to node A, which means there's an edge connecting them to node A. In this case, that's nodes E and node G. We're going to then ask, are either of node E or node G the destination? In this case, no, we're looking for node B again, so we're going to mark both node E and node G as visited. Then we visit the nodes adjacent to nodes G and E, which in this case are nodes C and H. We once again ask ourselves, is this the destination? No, it's not. We mark them as visited. And then we go on to visit the nodes adjacent to node C and node H, which are nodes B, F, and D. We then ask ourselves, are any of those the destination? Yes, it is. Our destination is node B, and we have found it. From this, we learn that there is a path from node A to node B, which takes us from node A to E to C to B. Now let's look through an example of this on a tree-like data structure. In this case, we're looking for a path from node A to node E. We do a similar kind of setup. We start the exact same way at our starting node, node A. We ask ourselves if it's the destination. No, it's not. Then we go ahead and mark it as visited. Then we visit nodes adjacent to node A, which are of distance 1 away from node A. These are nodes B and C. We again ask ourselves, are either of those a destination? No, they're not. And then we mark them as visited, and then visit the nodes adjacent to both of those, which are node D and node E. We ask ourselves, are either of them the destination? Yes, it is. We found node E, which was our destination node. From this, we learn that there is indeed a path from node A to node E, and it is from A to B to E. And finally, let's look through an example where there isn't a path between the two nodes. In this case, we're looking for a path between node A and node F. We go ahead and once again start at node A. We know it's not the destination, so we mark it as visited, and then we move on to the adjacent nodes, E and G. We ask if they're the destination, they're not, so we go ahead and mark those as visited, and then go to their adjacent nodes, C and H. We ask ourselves, are they the destination? No, they're not, so we go ahead and mark them as visited, and then visit their adjacent nodes, B and D. Once again, ask if any of them are the destination. No, they're not. Mark those as visited, and there are no more adjacent nodes to either B or D that have not been visited. So what do we learn? We found out that there is no path that exists from node A to node F. Next, let's talk about some of the properties of BFS. First off, its time complexity is O of the cardinality of the set of vertices plus the cardinality of the set of edges. What this means is it's effectively bound to the number of vertices plus the number of edges. This is because in the worst case, we end up going through every single vertex and taking every single edge in our graph. The space complexity is O of the cardinality of the set of vertices. This is because we need to keep track of the nodes that we've visited. The way we do this is by storing them inside of some kind of a structure to maintain the list of visited vertices. This could end up being the entire graph and therefore contain all of the vertices. The final property of BFS is that it finds the shortest path from one node to another if the edges are unweighted. By unweighted, we mean that for any vertex, the cost of going from that vertex to any of its adjacent vertices is exactly the same. Therefore, if the cost of going from any vertex, let's call it X, to an adjacent vertex is different than the cost of going from X to another one of its adjacent vertices, it will not find us the shortest path. The best way to think about this is that BFS finds us a path that requires the least number of edges to get from the starting node to the ending node. And that is the end of part 1 of my 3-part guide to breadth-first search. If you ended up liking this video, please share it with a friend and leave a like down below. These are free and easy ways to support my channel, and subscribe for parts 2, 3, and much more content down the line. In part 2 and 3, we'll be talking about how you code this algorithm in Java, as well as give you some interview tips, so stay tuned for that. Anyways, until next time, see you.